Alright, now we're going to discuss continuity and one-sided limits. Now with continuity, you already have an idea of what a continuous function would look like. For instance, I'll draw some functions up here. And a hole in this one. I'll put a dot down here. And I might as well do a step function. Now if I were to ask you which of these is continuous, just by your everyday usage of the word, you would point to this one and to this one, I'm sure. And you would say, well, this one's not continuous like these guys are, and neither is this, and these other two are, I would say, not continuous. So that's correct, and that's pretty much all there is to it. But there is a formal definition, and there are a few terms that go along with it. So I'm going to write a few things here. This is continuous. We'll just say it's continuous. That's continuous. Okay, so this NR, we'll look at these NR ones. Actually, let's start by looking at these ones. This is what's called, they're discontinuous, but they have what's called removable discontinuity. Because you can remove the discontinuity easily with a single point. If I fill in this open circle, now I've defined it, and it's all continuous. It's all connected together. So I fixed it, and I fixed it with a single point. I can do the same over here. And I would have to erase that. But now it's gone, and I fixed it with a single point. So that's what's called removable discontinuity. This one, I can't just use a single point to fix it, so it's called a non-removable discontinuity. So, kind of some funny words, but they're necessary because it's math. Okay, so let's put over here in a box a formal definition of continuity at a point. Okay, so a function f is continuous at some point c if three things are true. F of c is defined. Okay, so let's look at some of these. So imagine I haven't removed their discontinuity. Let's look at this one right here as this one looks right now. Imagine this point was never here, and all that this is a line and a hole and a line, and this one as well. The problem with this one at C, if this is our C, which our I immediately goes to it, it's discontinuous at C because it's not even defined as C. The function doesn't even exist. Same here. At this C, there is no function. It doesn't exist. So that would be one thing. I mean, if there's no function to speak of, then of course it's not going to be continuous. It'll be discontinuous. Okay? So then the limit as x approaches c of f of x would have to exist. So if the limit exists, then great. Let's look. Let's put this point back in here. Now I've got an example here. Everywhere it's defined, there is a function here. It just kind of jumps down here for a split second and jumps back up here. So it's defined everywhere. So condition 1 is met. And actually, the second condition is met. So let's look at this step function. There's lots of different points of interest on this one, lots of C's that we could look at. Let's say this one. Here's C. So again, it's everywhere defined. When I come here along this line, this is the function up until this point, and just as I get past this point, I jump down here, and it's defined as being here, and then it's defined here. So everywhere I can find a function, I can find a y value for the function. But at this point, the limit doesn't exist. As I approach from the left, let me get another color. As I approach from the left and I approach from the right, I'm approaching different values. So the limit does not exist here at this point C. So condition 2 is not met. Let's look at 3. Condition 3 would say that the limit, we're talking about the limit again, as x approaches C of f of x, not only does it exist, but it equals f of c. Which means that, yeah, there's a limit, and to find that limit, I could just put c into the function, and the y value is the limit. Okay, so let's go back over here. Everywhere defined, there is a limit at c, but the limit is not equal to the function itself at c. The function's worth like -2 or something, and the limit would be, let's call it 1. So the actual function is worth -2, but the limit is 1. That's not equal. Right here, the limit as x approaches c of f of x is equal to 1, but f of c is equal to -2. So condition 3 is not met. Okay. Now, if we talk about continuity at a point. We say it's continuous or it's discontinuous at a point. We don't say a function is discontinuous overall, because look at this guy. This guy, look in between these 2 points, everywhere in here, it is continuous. Okay? So let's take this one because it's fairly clean. There's not a lot of stuff written on it. Between A and B, but not, pay attention to this, is on an open interval, not necessarily right at A and right at B, okay? But everywhere in between A and B, not including A and B. So on this interval, right, this interval, open, that's the round parentheses, means an open interval, we say that it's continuous on this open interval if at every single point inside the interval it's continuous. If any c that we choose inside here, it meets these 3 conditions, we say that it's continuous on this interval. Continuous on the open interval. You might ask about a closed interval, and I'll define that in a second here. So there you go. That's another thing. And for this one and for this one, right? Because all these here have these points or these intervals that they're continuous on. This one from here to there, from there to there, and others. Not just that, and even this one for a short time is continuous. But these ones, since we assume they go on forever and they're going to be continuous forever, we just say they're everywhere continuous. So if they're continuous on this interval, we call them everywhere continuous. Just some vocabulary. Everywhere continuous. Now with this discontinuity, at times it is useful to talk about limits in a different way. So I'm going to draw a function that has discontinuity because the limit doesn't exist. Okay, so at this point C, we can see it's discontinuous at C because there's no limit. So that breaks up the continuity of the function. I'm just going to write some, let's call this function f, write some notation up here. Here's C. Let's make this -2. This is +1. So this, I'll say, the limit as x approaches C, but with this new notation, this is 1. With this new notation, it's -2. So this is what we call the one-sided limit. And it's pretty straightforward that the side that this is coming from is from the negative side. From the left-handed limit. That's what we call it, the left-handed limit. And this would be the right-handed limit. So we'd say something like the limit as x approaches c from the left of f of x is 1. The limit as x approaches c from the right of f of x equals -2. Okay, so that's just really nothing more than some new notation and the idea of a one-sided limit. Okay. Now, I want to pose a problem to you. Let's say you're a mountain climber, and say you start here on day 1 at 8 o'clock, 8 a.m. You start climbing, and you climb to the top, and let's say at 2 p.m. at the end of the first day, you get to the top. Okay, and then you take a rest. You sleep the night there. You camp out under the stars and that kind of thing. And then the next morning, this is a new day. Next morning, again at 8 a.m., you start out again. Okay, and then by 2 p.m., you're at the bottom. And here's the question. At some point on the second day, will you be at the exact same altitude at the exact same time of day that you were at that altitude the day before? So just for instance, let's say, would it have to absolutely be true that just maybe you were at this altitude at the same time of day that you were at this altitude the day before? Or it could be some other altitude. It could be right here. And of course, realistically, it's probably somewhere near the middle, right? Somewhere in there. It's necessarily, absolutely 100% true that you will be at the exact same altitude at the exact same time of day on day 2 as you were on day 1. And you can pause the video and think about it for a minute, figure out yes or no. What I'm going to do is first erase some stuff. So let's do that. Okay. And right underneath this mountain, I'm going to draw a couple functions. First, let's set these axes here. This is going to be 0 hours, and this will be 6 hours. You can imagine this is 8 a.m. or 2 p.m., whatever helps you, but this 6-hour span is the amount of both trips. Actually, let's make it 8 a.m. and 2 p.m. And this is 0 feet, and this would be, let's just say the top. Alright, so our first function, let's make it blue, and we'll call it f. Alright, and we're going to graph our climb, the climb of the mountain. And you could choose anything. You could pretend that you jumped, to the top, which means you would be ascending really quickly in a short amount of time, and then you climbed the rest of the way for the rest of the day, or climbed straight up this way, or let's say you made some real good progress, and then it was like a cliff, so you're not making much progress, and then it's really good. Then you take a break for lunch, and what have you, and you get to the top at 2 p.m. So here's what I want you to imagine. This next graph is going to be, for one thing, it's going to be red, and it's going to be the graph of your descent. So you're going to start here, right? You know that you start here at the beginning of the day. And the other thing that you know is that you stop here at the end of the day. Okay? And what we're about to visualize in our heads has a lot to do with the intermediate value theorem. It's not exactly the intermediate value theorem. And then after that, we're going to change it so it will be the intermediate value theorem. So imagine that you draw this graph of your descent. I challenge you to draw anything that doesn't violate the space-time continuum. that doesn't cross over this graph somewhere. At some point, whether you jump to the bottom and slowly crawl to the very bottom, or jump to the bottom right away, or hang out all day long, do nothing, and then jump to the bottom then, or make a gradual descent. No matter what you do, you are gonna have to cross this at some point. No matter what I do, I could climb even higher, right? But eventually I'm gonna have to jump down because I know that I got to the bottom at 2 p.m. That's what we stated before. So there's just no way to not cross that other the graph of your ascent. And I'm going to draw this so that for the next part it's a little easier to use. Something a little more realistic. Something more realistic, like we said before, would be that we crossed that other path, or that we were at the same height at the same time of day in the middle of the day, somewhere near the middle of the mountain, just to be realistic. Okay, so let's draw another graph up here. Let's draw it right up here. And this new graph is going to be f minus g. Alright, f minus g is going to be purple because it's these two put together in a way. So now we've drawn all this, but really what I'm about to say we could have realized from the very beginning. Knowing that there are two graphs of one of our ascent and one of our descent, we know that at the beginning of the day on the first day we were at the bottom, and at the beginning of the day on the second day we're at the top. So if I subtract g from f, and I should put g over here, is red. If I subtract g from f at this point, at the beginning of the day, I'll have a negative. Okay, so I know that I'll actually have a negative, top of the mountain. If this is top, we're looking at negative top right here. Okay, and then at the end of the day, on both days, I know that at the end of the day on the first day I was at the top. At the end of the day, end of the day on the second day, I was at the bottom. So if I subtract f minus g, I've got top minus nothing. I'm all the way here at the top. That's what f minus g would look like. And I know that for all those, all the in-betweens right here, f is continuous. Okay, this is a big part of the intermediate value theorem. It's continuous. Okay, and so is g. And one of the properties that we know about continuous functions that's pretty straightforward, and we didn't explicitly cover it, but if f is continuous and g is continuous, then f minus g is continuous. And that just makes sense, right? They both have values, they're both defined, they both have limits that exist, and the limit at c equals f of c, all these things. And so f minus g would be continuous. So here it is. Here's this point A, and here's this point B. Okay? And what we want to know, the original question was, do we cross our original path the same time of day, same altitude? Well, if I'm subtracting f minus g, I know that their intersection would mean that they have the same y value, which would mean that they would be 0. F minus g would be 0. They'd cross the x-axis. So we've got this point that's negative. We've got this point that we know is positive. We know it's continuous in between. Okay, intermediate value theorem says if you have a point here and a point here, not necessarily positive and negative, but here and here, different y values, and you know the function's continuous, and there's some value between a and b, then at some point it's going to cross that value in between a and b. And that may seem obvious, but I just like this picture of it. It just makes it so, and I like this problem. It causes a lot of controversy. So here we go, f minus g, it's going to look something like this, and eventually I'm going to have to cross that x-axis. right? So that's it. That answers the question definitively. Yes, you will have to at some point be at the exact same altitude at the exact same time on the second day as you were on the first day. And it also exemplifies the intermediate value theorem. If there's a point A and a point B, and there's a point C, let's say it's actually a y value of C in between those two values, and you have a continuous function between A and B, then the function must have, let's say that there's some x such that f of x equals C, right? At some point, our f minus g in this example is going to be at 0. It's going to cross the x-axis. Okay? Well, thanks for hanging in there for so long, and sorry the video was choppy. My computer kept crashing, but I think it might be better now. So, hope that was helpful.